All right, so the second fundamental theorem of calculus says if you have a function, and let's call this the f of t, that's defined on some interval that contains a. So we don't really care about the interval at this stage, we just care that a is in the interval. Then for every other x value in the interval, right, so these are x values, if you calculate the definite integral, excuse me, that's an f of t, on the interval between a and whichever x you choose, and then take the derivative of that, well, what do we know? We know if we have f of t, it's going to lead to the antiderivative of x, right? Because you go from a to x, and x is a variable, and a is a number that comes out in the wash, so you're going to get some function, which is the antiderivative of x. And then if I take the antiderivative of that, it's going to give me f of x. Okay, that seems almost obvious. It's because if you take a function, you take the antiderivative, then you take the derivative, we know we're going to get back to the original function. So how on earth is this useful, and how could this possibly be so useful that we would call it the second fundamental theorem of calculus? Well, let's do an example to see if it can start to make sense for us. So we have some antiderivative, which is defined as the integral, or the definite integral, from 0 to x cubed of sine t squared dt. What we want to do is we want to find the f prime of x. So we want to find the derivative of the antiderivative, which means we want to find the derivative of this. So we're going to want to use the chain rule, and we're going to do a substitution. So let me start by marking the substitution out. I'm going to let u equal x cubed, which means that du equals 3x squared dx. And then I can apply the chain rule before, just to make things a little bit easier to see. What we want is the derivative of f df dx, but I have a u in here, so I'm going to break this apart, which I'm totally allowed to do. df du, so the derivative of the function of the integral of the antiderivative with respect to u times the derivative of u with respect to x. Okay, so now I sort of have a place to work with all my different variables. I'm going to go ahead and make a substitution. Now remember, df du just means the derivative of f, but this is my f. So I'm going to substitute that in. I'm looking for the du of the antiderivative on the interval from 0 to x cubed of sine t squared dt. And then I'm going to follow up with my du dx. All right, so now I want to use the substitution. So I'm going to put in for du, or ddu, because I want to take the derivative with respect to u of a function, of the definite integral of a function with u, with respect to u. So I'm going to substitute my u for x cubed, and that leaves me with sine t squared dt du dx follows along. So now the whole reason for doing this was I've set myself up to use the second fundamental theorem of calculus. Let's write it down again. It says that if you have d dx, you're taking the derivative of the definite integral from a to x of some function in t dt. that equals the f of x. And so basically, d dx, you have an x in the upper boundary or limit of integration. I don't really care what this a is, right? I'm going to put in, I'm going to integrate. If I integrate and then I plug in x's and then I plug in a, this drops out. In the theorem, there's a proof in the book if you want to go through it, but in the theorem, this drops out, and all I'm left with is f of x. So that lets me rewrite all of this as just sine u squared. And now I have to write times du dx. Well, du dx is easy enough. If I divide both sides by dx, then I get du dx equals 3x squared. So I have sine u squared times 3x squared. And all I have left to do is resolve this u. So I have the sine, well, u is x cubed squared, is x to the 6th, times 3x squared. Cool. Now, why would I want to do that? It seems like that's a lot of work. But the truth is, let's look at just taking the integral. So I could do, I want the f prime of x. I'm looking for the first derivative of the big F of x. That's the antiderivative on the interval from 0 to x cubed of sine t squared dt. So at this stage of the game, I want to do something with that t squared. So I let u equal t squared. That's good. Du equals 2t dt. I want to substitute for dt, so I've got to divide by 2t. So du over 2t equals dt. And then when I go to substitute my u's in, I'm going to not change my variables of integration here, or my limits of integration. So I have sine of u, that works, and then du, because dt equals du, well, 1/2 I can pull out front over t. Well, that didn't help because I have that t. Well, t, if u equals t squared, maybe I could rewrite it as 1/2 0 to x cubed of sine u over the square root of u, right? Because if I just solved for t, over the square root of u du. Well, I'm in a weird place again, because I could write, that's 1/2 times 0 to x cubed of sine u times u to the 1/2 du. And now I could do another substitution. I guess this might actually work out for me. I'm going to let oops, sorry. Let me get my letters straight. Got a little enthusiastic because it looked like it might work out. dv, okay, way enthusiastic. V equals u to the 1/2. So dv equals 1/2 u to the 3/2, negative 3/2 du. That's not going to work either because I'm still going to have a u when I divide through. So I could go round and round and round. In fact, we're going to learn a technique that'll work on this type of integration. But for now, we have no way to find the integral of this or the antiderivative of this function. And so there's no way we can find the definite integral of that function except by using the second fundamental theorem of calculus. And that's that.